Welcome to lecture number 5, Noise in Communication Systems, in the course EEE 6211, Fundamentals of Communication Systems, one of the master's courses offered here at the University of Zambia. Now, data transmission occurs between the transmitter and the receiver over some transmission medium. This medium could be wireless, it could be wired, or it may be classified as guided or unguided. With guided media, it means that the waves are guided along a physical path. Basically, the signal is being guided along a physical path. And a good example of guided media, twisted pair, coaxial cable, optical fiber. So that's basically guided media. And guided media means that you don't have a physical link. All you have is a wireless path, which provide a means for transmitting radio waves. So in both cases, whether unguided media or guided media, you will have noise that exists. And therefore, it's important that we look at electrical noise even as it pertains to communication systems in this lecture. Now, by definition, electrical noise is defined as unwanted signal within the wanted signal, either inside the transmitter, along the channel itself, or even inside the receiver equipment. So noise finds its way, or basically can dwell in any of these equipment. Noise can be classified as external and internal noise. Those are the two broad categories of noise. Like I've said, external noise, this is noise created outside the equipment or outside the receiver. And examples include atmospheric noise, extraterrestrial noise, industrial noise, well as if we talk about atmospheric noise, this is noise caused by lightning discharge in thunderstorm and other natural electrical disturbances. Usually atmospheric noise tend to affect a wider spectrum due to its random nature. This noise becomes more pronounced when operated in the VHF range, very high frequency, 30 megahertz or above. Then you also have extraterrestrial noise. This is noise from solar and cosmic sources. Solar noise is noise from the sun. It can have a temperature exceeding 6,000 degrees, whereas cosmic is noise from the stars. So basically extraterrestrial noise has two sources there, being cosmic from the stars or solar from the sun. Industrial noise, this is noise from cars, aircrafts, industrial machines, and so on. It can range from 1 to 600 megahertz, and this noise can affect the transmitted baseband signal as well. Internal noise, this is noise usually inside the transmitter, inside the receiver, or inside the communication cables. It's basically a function of so many factors such as resistance, bandwidth, and temperature. And this noise is far more disturbing in communication systems than any other types of noise. And therefore, we'll discuss internal noise, especially as it pertains to what is known as thermal noise. In fact, internal noise can be categorized in terms of thermal noise, intermodulation noise, crosstalk, impulse noise, and shock noise. And so crosstalk, this is unwanted coupling between signals. It can occur between electrical coupling, between nearby twisted pairs. This is what is usually experienced by anyone who, while using the telephone, has been able to hear, some form of conversation interfering with the wanted signal. Impulse noise, this is basically non-continuous noise consisting of irregular pulses or noise spikes of short duration and of relatively high amplitude. It is usually generated from a variety of causes, some of which include external electromagnetic disturbances such as lightning or faults and flaws in a communication system. So impulse noise is generally only a minor annoyance. However, this may look small in analog systems, but in digital signals, that can cause very serious errors because that spike may change, digital data from a 1 to a 0, 0 to a 1. So impulse noise is quite dangerous for digital systems. Intermodulation noise, this is noise due to signals of different frequencies sharing the same transmission medium. The effect of such noise is to produce signals at a frequency that is either the sum or difference of the two signals. Thus, the derived signal could interfere with an intended signal. So the sum of the two signals can actually interfere with the wanted, or the difference of the two signals may interfere with the wanted signal. But far more worse, like I mentioned earlier, is thermal noise. This is noise due to agitation or thermal agitation of electrons. It is present in all electronic devices, transmission media, wherever you have conductors of resistance. It is a function of temperature, resistance, and bandwidth. Basically, there are three factors that affect thermal noise. That's temperature, resistance, and bandwidth. Now, in thermal noise, we normally talk of what is known as thermal noise power. Thermal noise power is basically proportional to temperature and bandwidth. So this thermal noise power increases with increasing temperature and bandwidth. And when we put an equality sign there, introduce a constant K, that K is known as Boltzmann's constant, and it's 1.38 times 10 to the power minus 23. Now, thermal noise can also be calculated given thermal noise voltage as Pn equals Vn squared over R. And we know that Vn squared, if we made it the subject formula, it will be Pn times R, and therefore Vn is the square root of Pn multiplied by R. But we've already calculated P to be KTB, therefore Vn is 4KTBR. The excess noise ratio ENR is nothing but 10 log T divided by 290 minus 1, where T is temperature in Kelvin. So if I know the temperature in degrees, convert that in Kelvin, divide by 290 minus 1, log of that times 10, what I'll get is the excess noise ratio. The noise figure is nothing but the ratio of the signal to noise ratio at the input with the signal to noise ratio at the output. Therefore, noise figure F is signal to noise ratio at the input divided by signal noise ratio at the output. The noise figure is a direct measure of the signal noise ratio degradation caused by the system, and it's a very important parameter in noise calculation. The noise factor is nothing but noise figure expressed in decibels. Therefore, NF equals 10 log F. So whatever value of the noise figure you get, which is F, express that in decibel, gives you the noise factor. Let's talk about data rate. The data rate in bits per second is the rate at which data can be communicated. Data rate can be computed taking into account the channel noise condition. Therefore, you can have data rate that takes into consideration noise and the one that takes into consideration of a channel that is without noise. Let's look at data rate for noise-free channel. For a noise-free channel, the data rate C can be computed using what is known as a Nyquist formula, and C is equal to 2B log M, where B is the bandwidth and M is the voltage levels or number of discrete signals. The log is to the base of T2. For a noise channel, C is equal to B log 1 plus signal noise ratio. Again, the logarithm is to the base of 2. And the signal noise ratio can be calculated given the signal power and the noise power to be 10 log PS over Pn, where PS is signal power and Pn is noise power. Let's do some tutorial. State the difference between frequency spectrum and frequency bandwidth. Suppose you have a noise-free channel, the bandwidth of 4 kilohertz. The voltage levels are 6, calculate the channel capacity. Number 2, suppose the channel capacity and bandwidth remain the same, but the channel experiences some noise, calculate the signal noise ratio in decibels. Look at question number B, question 2B. Given a receiver with an effective noise temperature of 290 Kelvin and 10 megahertz bandwidth, the effective resistance of this receiver is 10 ohms. Let's calculate the noise power, noise voltage, and excess noise ratio in decibels. Well, this marks the end of our lecture for today. Thank you for listening.